Okay, so here we're going to start out with just a little exercise here. So I want to draw a connected graph with 5 vertices and 5 edges. All right, now, so the goal here is going to see Euler's formula, or to introduce Euler's formula as it relates to planar graphs. Okay, so we'll do that by just this little activity where we're going to do this. Draw a graph with 5 vertices and 5 edges, and then from there we will focus on vertices, edges, and the faces created. All right, and then we'll add another edge and see how those values change. Okay, so let's start off here. So 5 vertices, so 1, 2, 3, 4, 5. Okay, so connected, so here, 1, 2, 3, 4, 5 edges. Okay, and now let's see here for our G1, vertex is equal to 5, edges is equal to 5, and faces we have 2, right? The one entrapped here by the connected graph here, and then the outer one, right? The unbounded one. So faces is equal to 2. Okay, so now let's go ahead and we're going to add a single edge to our graph between edges that are not already adjacent. Okay, so I can do that. There's a few different ways I can do that. Let me start by just doing this. All right, so now this second version of my graph, excuse me here. So vertex, still 5. Edges, I've added 1. Here, and now we have 1, 2, and then the unbounded one. Faces is 3. Okay. Okay. All right, and now here, let's take a look at adding one more edge here, where I still want it to be planar. All right, so here I can add this edge right here. So V is still the same, 5. Edges, I've added 1, so edge is 7. And then the faces, we have now 1, 2, 3, and then the outer unbounded face, so that is 4. Okay, and now we can see here that it looks like here the vertices and the edges, or the edges and the faces, once I add an edge, it kind of almost counteracts the face, right? So that also increases as well. All right, now as it turns out, there is a connection between V, E, and F. Right, and that is what we call Euler's formula. So Euler's formula, so this is for connected graphs. All right, for any connected planar graph, we have V minus E plus F is equal to 2. Okay, and we can see here that net change here in each step of the way is 0, right? So here we could state up here these examples that we have in each step of the way, right? V minus E plus F, so that's 5 minus 5 plus 2, so 2. Then we hear 5 minus 6 plus 3, right? So that's negative 1, 5 minus 6, negative 1 plus 3 is 2. And then lastly, 5 minus 7 plus 4. 5 minus 7 is negative 2. Add 4, we get 2. All right, so we could see how once we've set up our connected planar graph, an addition of an edge, all right, results in the creation of a face. All right, so here let's do a not a very rigorous proof, but just a sketch of what a proof would look like. All right, so we're going to start with a graph here. Two vertices, one edge. All right, so here V is equal to 2, E is equal to 1, and then F is also 1. Right? We only have that unbounded edge here. Okay, so now in this case, we could see, all right, V minus E plus F is equal to 2 minus 1 plus 1, which is in fact 2. All right, now if I start building here onto this graph, right, I could add a vertex here and then stray across here. Okay. Now for this particular case here, we've increased the vertex and the edges. But notice that since it's not bounded, we still have the same number of faces, that being 1. All right, so in this case, we have a net change of 0, right? Because I'm increasing my vertex by 1, right? And my edges by 1 as well. But notice in the formula, all right, V minus E, that's a net change of 0. Okay, so that still holds, right? 3 minus 2 plus 1, still 2. All right, so now this is really the way that we can build our proof, right? In any state of the graph, you can spike out here and add a new vertex and another edge, right? Or the other move you can make is you can create a circuit where you don't add another vertex, but instead you connect two existing ones with two existing vertex that are not adjacent already. All right, so what that does now, if you notice here, well, that increases my edge count, right? Vertices remain the same, right? That's unchanged. The edges are now increased by 1, but notice in doing that, I've closed it off and I've created another face. So again, the net change of 0, right? Because that increase in E comes with an increase in F, and that balances itself out in the formula. So we're left with 3 minus 3 plus 2, still 2. Okay? And this is essentially the sketch of the proof, right? Each step of the way, this is how we would kind of build our graph, right? Either by spiking out and creating a new vertex with an edge, or by connecting ones that are not already adjacent, and that results in a new face. Okay, so now moving on here, let's look at just a straightforward example. So let's say here for this example here, we have given a planar graph with V equals to 7 and E equals to 9. Find F. All right, so again, I know it's connected, or I know it's planar, sorry. And we'll assume that it's connected here. So using the formula, right? So we have formula V minus E plus F is equal to 2, right? Well, that means that since it is an equation, V is 2 minus V plus E. Okay, and we could say, so that means that the faces must be 2 minus 7 plus 9 here, which gives me a total of 4. So it must have 4 faces. Okay, so now let's see what that looks like here. So vertex, so we'll go 1, 2, 3, 4, 5, 6, and then 7. All right, and now I need 9 edges. We got 1, 3, 'Kay, so how many is that? 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay. All right. So here we have a graph, 7 vertices, 9 edges. Right, and as we can see here, right, we have 1, this space here, 2, 3, and then the outer unbounded one, 4. All right, and we could see here that no matter what I do here, as long as I don't cross the edges here, right, no matter in what way I move this graph here, that inequality is still going to hold, right? 1, 2, 3, and then the outer unbounded. Don't forget about that one, right? So that is 4. Okay, so just keep that in mind, right? There is more than one representation, right? And as long as it's still planar, no edges crossing, right? Once you do this, right, forget about it, right? That doesn't hold anymore. This concept of face is not valid. But as long as we remain planar, right, then that equation will always hold.